Today with Paulus for a lecture, which is titled A Boundary Perspective on Physical Processes.
Okay, thanks, Johannes. Yeah, so the aim of the lecture today is to try to show how to compute physical processes in expanding universe, generally for W cosmologies, without having to go through the time integrals through which, in principle, they are the Feynman diagrams in perturbation theory are defined. And this will be very important also to understand a little bit the structure of these processes. But before doing that, I think it's useful to make a small recap of the previous lecture. So what were the most important messages from the lecture of yesterday? The first one is that so the Bunch-Davies wave function has singularities just in sums of energies. I'm putting energies in quotation mark because I think it has been clear. It's a little bit of an abuse of language because there is not just such a thing as energy. These are associated to moduli of the moment of the spatial momenta. And so these sums can be either can involve either all the energies of the process or some of the external energies and some of the internal energies, which implies that second important message, they correspond to energies, to the total energy of sub-processes. For example, what it means, what we saw is that if, for example, I take the process in which from the vacuum we get a 4-point state with an exchange, this line as usual is the boundary at infinite future, and these are our external states, this is the internal one. The type of singularity that we can have involve either the sum of the external energy, the total energy of the process, so involve the full process. So this will be like E1 plus E2 plus E3 plus E4 equals 0. Then we can have another subprocess might involve just this vertex. So we'll have E1 plus E2 plus Y equals 0. Well, let me call that Y is defined as P1 plus P2, which is by spatial momentum conservation is equal to P3 plus P4. And similarly, the other subprocess is associated to this other vertex, where then the condition will be that Y plus E3 plus E4 is equal to 0. So this process will have singularities at these points. Okay. And another important piece of information is that all the singularities lie outside the physical region. Well, the physical region was defined by having all the energy positive, as well as all the internal energies positive. But this stays for internal, because in this case we have just one, but for more complicated processes you have many, but all of them are in principle strictly positive. So if we stay in the physical region, the only way that you can satisfy these conditions that they are individually zero, but then you get trivial processes, so you don't get anything interesting. You get zero. So you don't have any process. So in order to access them, you need to do a summative continuation to decide that some of the energies can become negative. And in that case, what one is doing is actually, rather than having just one type of states, one will have both in and out state. And for that reason, another thing that I showed in a concrete example, but it's generally true, as actually you could hear when Nim answered my question at the very end of his talk, that it's a general fact that then the coefficient of the singularities are associated to the high energy limit of flat space scattering amplitudes. So in this case, for example, what will happen is that when you get close to this point, you not only have in out state if you do this analytic continuation in order not to get something trivial, but then this condition means also that you are restoring energy conservation, and therefore what you have is that your wave function for this process will be something like the contribution to the amplitudes associated with the same graph. This is a G which stays for the particular graph. And then here you have the singularity, which depends on the specific background and states that you have. Sure. Okay, very good. Because a way to the way that this singularity comes about is because when you have these time integrals from -infinity to 0 of eta and times eta, you have this type of structure. What's happening is that you observe the singularity corresponds to when you in these integrals you go close to the region where eta goes to the infinite past. And so what's happening is that when eta goes in this region, if you don't do anything, you will get this which goes to 0, because I mean you have to introduce some I epsilon to regulate it. However, if your energy is 0 at the point in which this energy is 0, rather than having this exponential dumping, you will have an actual singularity. So the point is that the high energy comes from the fact that you are moving. So you're given that you have this in this region. So that having the total energy is equal to 0 means that you're taking all the process arbitrarily far away in the past, so you are taking it in the high energy region, because in the infinite past you go in at a higher energy. That's motivation. This also means that if you have some massive state, you're gonna get an amplitude for the correspective massless state. And actually, this is actually, you can make this type of argument even for when rather than considering the total energy, you consider just the total energy of a subprocess, and there you can see this the fact that when, for example, you're here, you got at this point, this again, you have a factorization between the amplitude associated to the subprocess, let me call it small g, times, and then you have, let me call it now psi tilde, which is a wave function associated to this other subprocess. So actually, let me call it psi tilde of g bar, so which is the complement graph, times the singularity, which is, and then you have singularity of some form. Okay. So why one was getting this factorization? One was getting this factorization because in this limit, if you remember the propagator, this bulk to bulk propagator has 3 terms, one which corresponds to the retarded part, the other one to the advanced part, and the other one to the boundary condition. And so what's happening is that in this limit, just one of these 2 terms will contribute. So let's say that contributes the retarded part. And therefore, what one gets is that here, this contains the mode function associated to this leg with the negative energy in this case, and with positive energies in this case. And so what one get is that this psi tilde that I wrote here is really 1 over twice the real part of psi 2, which is a factor which is in front of each of these terms. And then here one get the 3 level, the small process with minus the energy, the internal energy will come from here, minus, which is this minus, and then the same process, but now the internal energy which goes to the boundary, which now is described by the mode function contained in each of these pieces, as now here positive energy. Okay, so one discovered that there are some sort of factorizations. Okay, so like in scattering amplitude, where we know that when we cross singularities, we get some the amplitude factorized in smaller in a product of smaller lower point amplitudes. In this case, you see that when also you cross this singularity of subprocesses, your wave function factorizes, but now factorizes in a part which is associated to the flat space process, and a part which is still, let's say, cosmological because it's given by the wave function. Okay, so this is very important because this gives you an idea of what is the physical content which is encoded in the coefficients of the singularities. Which, in a sense, for example, if let's assume that we know very well what's the singularity structure of our wave function, we can actually use this information to try to bootstrap the wave function without giving the having to do this time integrations. Okay. Very good. There is any question about this? Okay. If not, okay, so far, I mean, what I say here are general properties with the only caveat that I'm making the assumption that the states I'm considering have a flat space counterpart. which, for example, if you are caring about the de Sitter, it means that there is a Wigner contraction for your de Sitter representation to some Poincaré representation, unitary representation. That's the only underlying assumption. Mm-hmm. Yeah, no, this okay, let's say that you have some state which fits in this condition I told you, but also you have some interactions of the type that you said. So if you have just this type of non-local interaction, then obviously the structure will be the structure, the analytic structure will be different because you have this non-local some non-local singularities, and therefore you might or might not have this pole. So in a sense, you can this is still valid, but just the answer is that when you try to go to this point, you get 0 because you don't have this a flat space counterpartist process.
Then you can't possibly.
Well, if you understand what's the meaning of this singularities that this non-local interaction introduce, then you might. For the moment, I don't have no, that's correct, but that just means that when you go to this point that I was talking about, either you get 0 or you get a softer singularity with a coefficient that can be some other something which is a purely cosmological effect, and then you have extra singularities which are given by the non-local term. And if you're asking the question, can I bootstrap it? It's really important that you understand what's the meaning of this extra singularity that the non-locality is introducing and what's happened when you approach it. No, but say in that case there are you need to be careful because sometimes and I think I'm not sure if it was the case of in Maldacena paper, but sometimes you can get these terms, but then you can make a field definition and you can get rid of them. If you can do that, this means that you don't really have this local term.
I think if you say for zeta, for example, the amplitude you get on the KP pole can be interpreted as an exchange of some constraint field. Like there's the Maldacena bispectrum you can get by taking a soft limit.
Yes.
4-point function has a well-defined amplitude in it. And when you take a soft limit, you're just exchanging the non-dynamical mode, like the Newtonian potential. So it has some amplitude interpretation when you exchange the constraint field.
Just do direct that the 3-point function. Then
yeah, so it's not an amplitude in the usual sense, but there's some object that has an interpretation where you exchange with some non-dynamic part of the measure.
Yeah, I think if you are asking the question about can I bootstrap this thing, it's important what David said, that you really need to have an interpretation of what this coefficient would be, or what happened when you so in the total energy pole, or what happened when you take these points. Okay, so yeah, so what I was saying, so far this what I was saying is general up to some caveat for which I've tried to be explicit about it. Now let's to understand a little bit more how we can do some computation. Unfortunately, we cannot be super general, so I think I will restrict to a class of scalar toy model. which are described by the following action. So it looks like massless states in flat space, but with time-dependent couplings. So this type of model, actually, if I declare that I have this time-dependent coupling is given by some number, which is the coupling constant, times 2 plus k minus 2 minus 1 divided by 2, where this an is the work factor in my FRW cosmology in conformal time. Then this model is describing a conformal couple scalar with in arbitrary FRW cosmologies and with polynomial interaction. Now, you can also generalize it by inserting a term which is like a mass term, which depends also on time. Okay, and again, upon the identification of this function of this mass, time-dependent mass with some function of the warp factor, this actually will describe a general massive state in FRW cosmology. Okay, I will restrict for the moment to this case for two main reasons. The first one is that there is for some specific massive states, we can actually recover the answer for the wave function from the wave function of the conformal couple. So I can compute the conformal couple, then do some operation and obtain that information. The second reason is that for general masses, which means in this, if you are in the sitter for states which are in the principal series of the unitary reducer representation of the sitter, which correspond to very heavy masses, then there is no real simplification in the calculation. You get some general some Hankel function whose order parameter is purely imaginary, and then there is, as I said, there is no simplification in the computation. So given that I won't try to argue how to so I will just restrict myself to those cases where it's clear how to simplify the computation, and therefore how to make actually this computation direct from the boundary. Okay, where here from the boundary, I just mean that what you want to know are just the information about, so typically this is our physical process. Your boundary information are the momenta. Okay, and then maybe the mass of the state which propagates, so the spectrum of your theory. Okay, so these are the only information that you want to have in order to do the computation. And the computation from the boundary, as I said one more time, means not to have to do the time integrals of which the Feynman diagrams are defined. Okay. So, for example, this Feynman diagram for this model will be given by an integral from -infinity to 0. Let me call this point A and B, the eta B. Then I have now a non-trivial vertex function. So I need to put here some lambda. In this case, I'm taking a fact cube, so lambda 3 eta A, lambda 3 eta B. Then now, given that the free part here is like a flat space massless states, my external states are described by just plane wave. So my mod function, which correspond to the bulk to boundary propagator, are just exponential. So I get e to the I e1 plus e2 eta A, e to I e3 plus e4 eta B. And then I have the bulk to boundary propagator here, G of y eta A eta B, which, let me remind, its explicit form was 1 to y e minus I eta A minus eta B, A minus eta B plus okay. So in principle, now, obviously, I should specify what are these functions. So I should tell you which cosmology I'm taking in order to actually do this, this computation. However, there is one of the goals also is to try to understand which properties of a process might actually be common to a larger class of cosmologies. So in order to avoid to specify the cosmology until the very end of the computation, one thing that one can do is to take these couplings that are time dependent. I'm not specifying what is this function, but I say that I want to consider an integral. Okay, let me write it a little bit slower. I want to consider an integral representation okay. I'm just doing that. If I do this, then this integral becomes and now I have my time integrals. Let me, for simplicity, you see that here the energy is associated to the states at the which go to the same vertex enter always in this combination. So I will call this big X1, this other one big X2. So now I get here e to the I big X1. But now, because of this integral representation, I have also this exponential. So one for each time integration. So this X1 is just shifted by this zeta A. And the same for the other. Yes, just one sec. And then the bulk to bulk propagator. Yes. Here. Yeah, because this goes back to the original condition that you want a bunch Davis wave function. So you have to pick the solution of your equation of motion, which are exponentially suppressed in the when you go to minus infinity, and which have positive energy solution. And these are why you get this. So it depends on the choice. That's actually one of the reasons for which also when you do the computation for the wave function, you also get a combination of positive combination among the energies. If you were to have different signs there, then that will also mean that you have in and out state, because the sign of the energy is also telling you in which direction the state is going.
So this theory you should think about, how should we understand this theory? And the effective theory, or the law of the theory, can we discuss so far you just think about these, but once I start going to the work, we want to meet with the mission about what happens to distance, session from one of the and the point how is it going to understand this?
Can you say it again?
Once you have polynomial interaction,
Yes.
in theory cannot be self-consistent.
Okay.
Therefore, how is it supposed to understand the whole framework? As soon as you're dealing with the key, there's no question now. But once I start going to this problem will be clear how it's supposed to understand the action. Like effective action or scale or
Okay, actually that's actually, are you actually saying that any polynomial interaction is actually non-normalizable? No, sure. No, I mean, okay. Let me put in here. Actually, the statement also depends on the dimension. Here, I'm trying to make a general picture in which I'm considering arbitrary dimension and you know, anything that in principle you can add there. Then obviously you have to be careful about the normalization issue. So you can maybe fix your computation to cases where your theory is normalizable. Let's imagine that we are in 1 plus 3, so in 4 dimension. If I choose this to be 4, that's fine. Okay, so I'm saying as much general as I'm trying to keep myself as general as possible, because there is some part of the computation that just does not depend on this issue. But obviously, at some point, you need to make some choices, and you need to be to specify what you're interested in, and then all these issues that you are specifying come in. So.
Yeah, and that's fine. Yeah, just the same.
Okay. Yes.
So this could also be described with a more generic time-dependent coupling of the component. I mean, it doesn't have to be the theta invariant or dilatation invariant.
No, but I'm not. If no, that's correct, because in principle.
Arbitrary time-dependent coupling.
No, you can do, but if you want to introduce to go from conformal couple to massless, you have to introduce a time-dependent mass term with a specific form. No, but what I'm saying is that you need to have some specific form here that tells you that then altogether becomes the massless state in the sitter. Okay. So no, you can do it. The only reason for which I'm restricting to this is that it's simpler. And for example, in the case you want to study the massless solution in the sitter, I can actually deduce them from the conformal couple by acting with some differential operator. Okay. So that's the reason for which this is a simple enough model to make some point. Then there is this generalization you can do to go to more general type of states, of mass scalar states. And about this, yes, for the type of interaction, you don't. I cancel it, but the coupling in principle time-dependent coupling. The only thing that you require is that it has this form with this number here, k minus 2. This is a minus d minus 1 half. Okay, so here this is the work factor for your
This doesn't even happen to the case.
no, that's correct. The only thing is that in fact, I mean, one of the whole point of doing this is that now you have this piece. This is probably what you want, you're trying to argue, that does not really depend on the specific cosmology. And then the specificity of the cosmology will enter when you have to do this integration. So there is a number of information that are completely common to any type of cosmology and comes from this integral. Yes.
But in this case, I think it's maybe more complicated, no? Because the fact that we have derivative expansion in terms of expanding amount by the derivative by cutoff. But here, you have this case, but then you go back in time to field also.
Yeah, the expansion parameter is the age of the cutoff instead of.
And is it that works the same? Is the yet to power counting work even if you start computing loops in the same way as that?
Age of the cutoff, yes. But it's always age, no matter what the momentum of the state is. If they're very long triangle, very short triangle, very small triangle, remember always age of the cutoff is the power. That's the subtraction of high dimension. It's very different. But space you can decide the energy here, you cannot decide the potential.
No, but the EFT power counting is not the next step, you start computing this.
As long as there is separation of state and that variable, you're good. But you're right that there's something to discuss.
But even in fact space is not completely clear because just to cut off regularization with EFT power counting is something to start. So it is in the right. Now. But here it's not like, and we're not really scattering here. So it's not, so there's no fixed energy chain as we said, the energies are like humble. So that's here, and these are correlated. Yeah, there are some sort of
yeah, very good. Yeah, so okay, so here, so in now, so the whole point now will be to try to develop techniques to actually compute this object, and then at the very end do this this computation, choosing whatever cosmology you prefer. In principle, this is probably this is where the expression that Guillermo was writing yesterday come from. If you take the warp factor to have this type of form, so maybe some gamma, okay, where L is the length, the length scale of your spacetime. Then when you do this Fourier transform, what you get is something of this type. Of this form, which is from 0 to plus infinity, is z z to some power beta minus 1. Okay. So now, but in general, you might decide that not to care about the specific form and just try to infer as much as possible from this integrand that actually, if you realize, is really similar. It's really like the flat space wave function. Because again, all the specificity of the cosmologies in these couplings here. And but in this case, that become an integrand, let me say a universal integrand for an FRW cosmology, for an FRW wave function. Okay. Now, another thing that one can do is then I can just make a shift of this variable of integration z in such a way to absorb this x in the measure. So let's say that let me declare that x1, small x1 is za plus big x1, and small x2 is zb plus big x2. Then what you get is now this lambda tilde depends on small x1 minus big x1. And then now we have something which really looks like explicitly what we saw for in the example yesterday, that it was an explicit example in the case of a flat space wave function. Okay. Very good. Now, the statement now is that you can, so another thing that is important to observe is that I've been drawing this type of graph. Okay, 1, 2, 3, and 4. Now, this small x1 and small x2 are still related to the sum of the energies at this point in this in the states at the same vertex, which means that in any case this information come always in this type of combination. So I can actually avoid to make this drawing and just suppress the external the bulk to boundary line, map it just to this type of graph, and attach in the label small x1 and small x2 to the sides, to the vertices, and y, which is the internal energy, to the edge. Okay, and it's much it's going to be actually easier actually to do with when you analyze this graph. And now the statement is that the wave function can be computed by iteratively erasing an edge until you erase one at a time all of them. What this means? So how do you see this? Let's see. I mean, I'm going to prove it in this case, but the proof is completely general. But I don't want to get. I mean, it might be just confusing to do the general case. So I'm going to focus on this universal. Sorry, this is actually. I'm going to focus on this part. Now, let me take an operator, which is the total time translation. In this case, for this graph, it's just given by this two derivative. And now I can consider an integral that is just the same integral I have in time. But now with this operator that is acting on the full integrand, which is e to the small x1, a b, g. Now, these are total derivatives, and such that at the boundary, when you compute these things at the boundary, g vanishes, and when you compute it at minus infinity, the exponential vanishes. So the actual result from this integral is 0. However, I can integrate by part, making this operator acting on the external state. So I have just x1 plus x2 and the very same integral, which is psi g. And then I have this guy, the operator acting on the back-to-boundary or back-to-back propagator. That if you do the explicit computation with the explicit form, you see that is gonna just be given by minus e to the I y eta a plus eta b. Okay, which boils down to have minus so these two integrals now factorize, and one thing that you recognize is this is just a bunch of exponentials, so it's all external state, and so you can think this is like a contact interaction. So what you're really having here is that this part is a trivial graph, so a point, but now the energy is not just xa, it's xa plus y. And this is another contact interaction with the xb plus y, whose total energy is xb plus y. So this equation tells you that x1 plus x2 for this process is just given by erasing the internal edge and associating the energy to the internal edge to both its endpoint, the endpoints of the edge. Okay, so in general, this is a much more general situation. So I can take this other graph, okay, which corresponds just an exchange of two states, and do the same computing by just saying that x1 that this is given by 1 over x1 plus x2 plus x3. If you will have to reiterate this procedure, you will see that you will obtain a two-term expression, which is x1 plus y. If I erase this leg, let me call this y1 2 y2 3. Then you have this other subprocess plus and this also works at loop level for the integrand of the loop. So you still will have to do the loop integration. Okay, so this actually can be made in terms of a recursive expression for in terms of in a graph theory language, in the sense that the way that you can, for example, compute this graph is by saying that you take a graph and then you associate the total energy. You take a subgraph you associate the total energy of that subgraph. Then you look at that subgraph, and you take again, you divide it in a smaller subgraph, and you associate to them the total energy. What this means that in this case, the first graph is the first subgraph of the graph is the graph itself. So I can associate to it the total energy. Then I look at it. There is just a way in which I can divide this into subgraph, which is this two, and I multiply this by the energy of this subgraph. This now is y plus x1 and x2 plus y. And this way, rather than having this three-term expression that you will have had by doing the explicit computation through the time integrals, you have on the nose the one-term expression for this graph that you obtain when you massage it. And again, I can give you directly these graphical rules, and it's a recursion. So this is telling you substantially that you can compute recursively a graph in terms of sum of products of a smaller graph. So if you know the information about the most basic building blocks, which will be the contact interactions, then going up, well, once you break this in all the pieces, then going backwards, you can actually reconstruct the full information of the wave function associated to this graph. Okay. In this sense, this is a way of computing from a boundaries perspective, because the only thing that you have to know are these energies associated to the graph that you want to compute, and then you just are dividing this smaller subgraph, which again contain information associated to the external the boundary information associated to those subgraphs. Okay. Yes. Yes.
Just to see that did you give the exact result or the result of the contact?
No, this procedure gives you the full result, because what it's telling you is that, let's say you said you want to compute the exchange, okay? Now, the statement is that the exchange graph is equivalent to, if you multiply it by the total energy, that is just equivalent to the product of the two contact interactions, which are whose energies are given by the original energies shifted by the energy of the internal state. So what you're doing, it's like erasing this leg and associate the energy in the internal energy to each of the contact term. Because in the bigger terms, it's like you're saying, for example, if you are taking this interaction, it's like you're saying you are erasing this and bringing this to the boundary, but with the energy with the same sign.
I get confused how it knows about the poles.
I think the conclusion is that maybe has in mind to analyze the calculation in terms of the number of external layers, while you are analyzing it in terms of the number of vertices. So if I ask you what is the thing with 4 external layers, then Paolo would say there is one contribution with one vertex that you already calculated at the beginning, plus this. And I guess David is saying, yeah, okay, the one with the single vertex is an independent, there are 2 coefficients, single vertex and a double vertex. So this calculation tells you the double vertex, but the single vertex is another.
I think I haven't understood what's the confusion. Okay.
Have really a contact. Let's see, have a fight. Really have a contact interaction.
Yes.
So then the 4-point function will have contribution of that also.
So yes, what they're saying is here you're doing the lambda 3 coefficient, but you need to put that also the lambda 4. No?
That you won't get from it by that.
No. Okay. Okay. No. Obviously. Okay. Let's say this procedure works wait, here in principle. Okay, obviously it depends on what you want to do. if you're in your Lagrangian, you think that you have, or you want, f(cube) interaction plus f(4) interaction. Obviously, this gives you the information about the exchange part, and then you will have another contribution, which is the counter term associated to the. But the point is that they have different couplings. Okay, so the lambda3, lambda4. So you can also compute independently in the sense that you can do this computation and then add them together.
The information about 3 point. So it's not like this here.
No.
Point,
No. Okay, no, wait a second. In BCFW, the fact that happened with some YAMLs, in principle, you have a 3-point vertex and a point interaction and 4-point interaction. But the coupling is the same. So that fact is a gauge artifact. You can make a field definition which you can absorb it. So there is really one fundamental vertex, not two. Here instead, if you want to say that here you have 2 different couplings, then I can always tell you, okay, for some lambda, you do the computation. For the other lambda, you do computation, and then you add the relevant contributions. So was this the problem, David, or?
This is the flat space, right? So
Yeah, as I was saying, I'm taking the procedure that I did is taking the integral, the graph for an arbitrary FRW cosmology, do this manipulation on the time-dependent couplings in such a way, or if you want, in time-dependent part due to the warp factor in such a way that I can map it in an integral over the external energies of a flat space object. And now I'm playing with the flat space object, which now works as the integrand of my final FRW process.
I think I was confused about the KT pole, which sits on the left-hand side, it's x1 plus x2.
X1 plus x.
You multiply by KT.
Yeah, I mean, what you will do, you can put it here, but that doesn't really change.
Yeah, there's only a simple KT pole.
Yeah. In this case, just looking at this integrand, this actually is for me another motivation to split the computation in this way, is the fact that precisely you're going to get always simple poles. So all the analysis is way easier. But obviously, once you want to do, if you let's say you want to do the final computation in a given cosmology, then you have to do those integration, and then the point becomes to see how that integration that you have to do, the counter integration that the counter integration intersect the eventual singularities that you can have there. So or in any case, how the singularities of the integrand can get mapped in the singularities of the final transcendental function that you might get. Okay.
Let's do it on the 3-point function. If I do a field definition, shift the 3-point function by something that's purely local, it doesn't have any model. How would that affect this computation? Is that then in the 4-point function, give me something else?
Okay, so in a sense, if you do that, I think you will get some term, because if you see, one of the features of this is that the degree, so you can get a rational function, and the degree of the polynomial in the numerator is always lower than the degree of the polynomial in the denominator, which means that typically the information about the poles is going to be enough to fix it. If you do a field definition, you're going to have some extra term, which actually can have not have the structure. And so in a sense, this shows can be some sort of canonical choice of what's the field definition that you're considering. So you won't be able to see these other terms. In fact, for me, for that reason, I have still this question in mind that for some cases that Enrico specified in his talk, it's solved, but for a general quantum field theory in curved space, at least I don't feel that it's solved. How can distinguish different wave function of different correlation function in the sitter or whatever for the cosmology, which differ just by free definition, or what's the invariant content of this? Because I think the case that Enrico you studied, it's a very specific case, and so that statement is true just for that case. The fact that there is no really field definition ambiguity. Okay. Very good. Yes, sure.
So far, this manipulations you've done is really much the analysis in flat space time, no? Power of doing this separating. So now when you do you still have a couple of integrals to do, right? If you want to know the full thing.
Yes.
And they contain the information about the cosmology.
That's correct.
And so can't you have, is it easy in general to do them, or in most cases that becomes?
Okay, so when you do, let's divide the answer into parts. Let's stick to the three-level contribution, okay? For the three-level contribution, you have just this integration over this axis to do. And obviously, the difficulty in doing them depends also the cosmology that you decide, that you choose. Let's choose for fixing ideas a cosmology which is defined by the work factor of this type. Okay, so gamma is some positive number. Okay, the measure of this integral. So I can write actually this integral over from x1 to plus 1 over small x1, then becomes something of the type small x1 minus big x1 to some other powers b minus 2, and the same for the other. Okay, so for one thing that we have shown that for some choices of this beta, okay, it's always at least equal 1 from it's equal or greater than 1. For some choices of that beta, then actually this you can actually do this integral, and you get polylogarithms. And there is actually a technology to extract those information even without doing explicitly these integrals, which is in terms of what are called symbols. You can extract the symbols, and then they are not defined uniquely, but there is a consistency condition here to fix the ambiguity. Okay. Now, if you then give me some crazy function, there some crazy measure, then obviously I don't know. But for reasonably enough type of cosmology, there is some systematics in which you can do this. Now, the second part of the question is that obviously this is at 3 level. At loops, you will have these integrations plus the loop integration. So if you just do this integration, you do the same, you get just polylogarithms. But then you have to do the loop integration, and there is not really known yet. I mean, there is not much computation done about it. But in principle, yeah, but here the point is that you are mapping a problem to another problem, for which we can think to actually recycle techniques that have been developed in the amplitude context. Okay.
But gamma in your equation is 1, what is beta then?
For if gamma is if gamma is 1, beta in the sitter. If, well, you have to also tell me, because if you have phi to the cube or something, so let's say that you have gamma is equal 1, and you have a phi to the cube interaction in 3 plus 1 dimension, then this is also 1, so that's easy. And this is actually where most of the test has been done. But then these other ones are also related to this.
So you're saying the sitter is the easiest case?
The sitter is the easiest, but then if you change this, you can have other value for this integer. This is still can be done. Obviously, again, there are more or less difficulties, depends on the value of this beta is. You might the point is that for some values of this beta, you might get IR divergences are here plus infinity, which actually correspond, even if for energies going to infinity, they are infrared divergences. The reason being that this really is telling you, remember that comes from a Fourier transform of a coupling, but that x go to infinity really means that you are approaching the boundary r eta equal 0. For the reason that actually is encoding infrared divergence due to the large volume. Okay, so the point is that in this case that I specified, that is what we worked out mostly. You are safe because you don't have this problem. Okay, this integration of this at plus infinity, you don't have these divergences. If you change that, you have to deal with this infrared divergence. Okay, so given that I think I have 3 minutes left, I think here the moral of the story is that you can take for some quite large class of scalar model the wave function in FRW cosmology, map it in an integral over an integrand which is substantially a flat space integrand, a flat space wave function, do manipulation on that integrand, and then do the integration. And the manipulation is really reduces to a graph theory operation on the graphs, okay, which are expressed in terms of recursion relations, okay, which means that if you have a big graph, you have to erase an edge at the time and sum of all the possibility that you can erase one edge, okay. And this is very important because here one thing that is making manifest with this is the fact that at each subgraph there is a singularity associated to it. So this total energy singularity is associated to the subgraph, which is the graph itself. These other singularities that are associated to these other subgraphs. So there is a correspondence between, which is very important, subgraph and singularities of the wave function. Okay, and then when you do the integration, actually these singularities are going to be mapped to singularity to the integrated function, but now rather than being the small x's and y, we're going to be in the big axis, which is actually the real external data. And I think I can stop here. If you have more questions ahead, otherwise, I guess we can go for coffee. Sorry.
¿Cómo es que la elección de la cosmología te fija entre estas integrales que tienen que ver con la función? ¿Cómo dependía el coupling de esta?
Sí, pues el cap.
Primero también entendían como esas integrales, pero evidentemente no.
No. Bueno, si quieres hacer los integrales, luego lo tienes que especificar. Lo statement es que tú tienes esos integrandos, tienes que integrar sobre una cierta medida. Esta fórmula es general. Pero luego, si quieres la función concreta, me tienes que decir que con la cosmología que tienes, que significa que couplings
Sí,
tiene.
bueno, esa es la elección de
Sí.
valor de gamma.
Gamma igual a 1 sería de Sitter, por ejemplo.
No, la elección de beta, digo, porque había entendido que es...
Sí.
de esa.
Sí. No,
Depende de cómo...
No, correcto. Ho puesto beta por no escribir el número grande, la expresión grande, porque si no, tú, de nuevo, tú tienes este tipo de expresión. Entonces, si yo pongo esto lo que tienes aquí, here, el gamma. Entonces, beta.
Esa elección, ¿por qué crees que tenga de esa manera de estar?
No, es una de las cosmologías que interesa a la gente. Esta es una posible elección. No tienes por qué hacerla. Tú me puedes. Si tú eliges algo así, por ejemplo, por alguna razón tú quieres algo así, con gamma positivo, realmente los integrales lo puedes mapear en derivadas, entonces es hasta más fácil, ¿vale? Pero sí, si tú, no sé, me das un arco tan, piensas inventarte cosas más complicadas, evidentemente es integrales, pero esta, decimos, es una cosmología razonable que la gente mira.
Pero esa es la cosmología, la pregunta es el capi, porque este es como que hace el campo escalar.
Porque no es una elección, es que si tú empiezas desde la acción, sorry, let's switch to English. If you take the actual action for conformally coupled scalar in with the polynomial interaction in the usual way, which means that you have your Lagrange. No, it's a realization of the fact that you have something like this in principle. And then here it's not, that doesn't depend on time. And so here you have the conformal coupling, and then, for example, you have this. Now, one thing that you want to do, put this in the form that I wrote before. So in principle, here you have powers of A. So what you do is some redefinition like this, in such a way that you absorb the dependence of here, but then you transfer, this gets cancelled, you transfer here. So that this number here, okay, is due to this mapping. So that particular choice of that number. Okay.
So in this original formation, that lambda was just a constant. It just gets a function.
Yeah, it gets a function because what you do, making it up. No. It's you can do it generic in the sense that if you are not worried about cosmology, say I want to study some problem with the time-dependent coupling, and so you can do this in any case.
Now I also understand why, because also your propagator is so the same, so it doesn't depend on because you just absorb the.
That's one of the tricks, yes.
Just one question about this differential operator that's
Yes.
allowing you to do this. Like, is it really teach? I mean, is this the consequence of the fact that you could, with like take the graph and the boundary it's attached to and modify it anywhere on the time chain? Is this?
It's really a consequence of the fact that you are using, this is a time translation operator, okay? But your theory is not time translation invariance. So what it does is, because if it were time translation invariance, it would be identically zero, okay?
So is it telling you that including the boundary, you can take anything, like, you have to shift the boundary as well? Is that what it's telling?
No, it's not telling you. It's just telling you that the really important contribution come from really the boundary. So that's the thing that, because at the end of the day, what this is telling you is that, because you see, in this computation, you get your original function that you want to compute, and something for which the only contribution from the bulk to bulk propagator that you get is from the boundary, which actually allow you to split it. So in a sense, it's what is telling you that the information of a big graph is encoded by putting some of the the bulk to bulk propagator to the boundary. That's what it's telling you.
I see. It's not telling you something about translating the full graph by itself.
No, the fact that you choose that operator, in a sense, it's a trick, because precisely you know that there is 2 out of the 3 times of the back-to-back propagator that are going to be cancelled.
Correct. Yeah, exactly. That's you could have probably played this trick with any integral with a g which disappeared at the boundaries, right?
Yeah.
Madonna, andiamo fortissimo in queste lezioni.
Say something.
Hello. Prova. Does it work? Prova. Excellent.
Well, you should ask someone.
I think the microphone is good, and I'm about to switch on. He's an optimist, 23. You have 25 minutes plus seconds. Okay. Okay, welcome back to the second session. So as you know, unfortunately, we had a change in schedule because Nima had some flight problems, but we're very lucky to have a speaker that could chip in and talk us about some exciting subjects. And so we'll have Paulo. It's me. I'm so sorry, it's recorded. It's recorded. We'll have Giulio tell us about positive geometry. He'll give a very gentle introduction to positive geometry. And there's a lot of papers coming up, so
Yeah.
I'm very excited about that. Giulio, take it away.
Okay, thank you very much. So I will do my best to make up for the missing of Nima. I don't know if I will succeed, but at the very least, I can guarantee you that I will be done in 25 minutes. So, and it's not because I do not have enough things to tell you about, but it's just because I thought that maybe this is a topic that is not entirely familiar to most of you, positive geometry. Although it's something that comes from the world of scattering amplitudes, but since the seminal work of Nima and Paolo, they have made an appearance also in the context of cosmology, and I'm given to understand that it's becoming more and more applied there. So, as the title says, it's going to be a very gentle introduction, and Paolo informed me that he will tell more about this stuff in the coming days. Okay, so suppose that we want to compute a scattering amplitude. Then we know what is that we have to do. We sum over all possible Feynman diagrams. But of course, this is an unsatisfactory expression for the scattering amplitude, because there are many situations in which the scattering amplitude is a very simple object. It's a very simple function of the kinematics, while the representation as a sum over Feynman diagram is a monster. The reason for this unnecessary complexity, well, there are many reasons, some which are more subtle than others. Sometimes the reason is that the scattering amplitude is simple because it's constrained by symmetries that you didn't know about, things like dual conformal invariance. And you didn't know about them because they were not manifest from the Lagrangian point of view. And because they're not manifest from the Lagrangian point of view, they're obscured from the tool that you get out of the Lagrangian, which is the representation as a sum of Feynman diagrams. So the amplitude is simple because it's constrained by this symmetry, but the symmetry is destroyed by the Feynman diagrams, and so the expression on the right has to be complicated. There are less surprising reasons for which the same phenomenon happens. It could be that you're working with a gauge theory, and then the amplitude has to be gauge invariant, that you know. But even so, each Feynman diagram individually is not gauge invariant. And so for the same reasons, there must be a very complicated pattern of cancellation between a non-gauge invariant object that produce a gauge invariant one. But I would say that there is an even more elementary reason for why this phenomenon happens. And I have to say that elementary is a word that is going to be recurrent in this talk. And the reason is locality and unitarity. So Feynman diagrams make manifest locality and unitarity, which I will make more precise. Let's consider a very simple theory, cubic planar scalar theory. Then an amplitude in this theory, as we know very well, can have a singularity only when the total momentum carried by a collection of consecutive particles goes on shell. So if we say, for instance, we have a P1 plus P2 plus P3 squared, and this is going to 0 in some massless theory. So this is a singularity, which means that the amplitude looks is blowing up, like P1 plus P2 plus P3 squared. This is locality, the fact that we have this singularity. And the residue of this pole, it's a product of simpler amplitude. The amplitude factorized into, for instance, a 4 amplitude times another 3-level 4-point amplitude. The factorization is what we usually call unitarity. Now, the need to make manifest both locality and unitarity require for us to produce the sum of the Feynman diagrams, because once we make manifest a pole, since we are factorized into other amplitude, this amplitude can have other poles. So you can, after you have gone to this kinematical limit, you can take another collection of particles and send them on shell. So it means that this amplitude has to factorize as well, this amplitude has to factorize as well, and you can do it in many possible ways. The only way to make manifest all these possible patterns of repeated factorization is by summing over Feynman diagrams, which is what you get when you factorize as much as you can. So this is the reason why, even if you start with a reasonably small number of possible factorization channels, something like n squared for a planar amplitude, you end up with a very complicated, with a very large number, roughly 4 to the n number of Feynman diagrams. Now, this also suggests that maybe you should try to find a representation of the amplitude. You could try to write the amplitude as a sum over the factorization channels. And you may wonder whether this gives the right result. Now, again, in complicated theories, there are many reasons for which this simple formula fails, especially if you have spinning particles. But even in this very simple planar cubic scalar theory, it's easy to see that something goes wrong. And it's just that you overcounted the possible Feynman diagram. So there will be a Feynman diagram that appears in a channel and also appears in another. So this is, again, the wrong result. But okay, this just means that this simple naive approach doesn't work. It doesn't mean that maybe you're not able to find a formula like this one, but you have to think hard. And let me oversimplify a little bit, but by thinking very hard about this question, especially in n=4 superior Mills, many representations of scattering amplitude have been found. For instance, the BCFW recursive relation. But then you end up, you find other problems. You have to introduce spurious poles. You have to understand the cancellation of those spurious poles. And long story short, the organizational principle that tells you what is going on, it's a geometrical object. In n=4, was first discovered in n=4 by Nima and Yara, and was called the Amplituhedron. It was discovered first in that theory, but then we have seen a never-growing list of examples where the same idea applies and the same description works, changing some details. So let me give you a very brutal simplification of this idea. The idea is that for every amplitude in your theory, there is a companion geometrical object, positive geometry, which is some geometry defined by the positivity of certain functions. So maybe you ask some linear function to be positive or some more complicated nonlinear function to be positive, and the region where they are positive defines some object. Now, this correspondence makes so that every amplitude is mapped to a geometry, and every possible factorization channel of that amplitude corresponds to one of the boundaries of your geometry. So for every singularity, there is a boundary. On the singularity, the amplitude factorizes, and correspondingly, the boundary of your positive geometry factorizes into the positive geometries which are associated to the factors of your amplitude. Okay. So before turning these nice words into an actual prescription to compute an amplitude, let me show you what I actually mean. So I want to show you an example of this correspondence between geometry and amplitudes. Again, in this simple field. So the theory that we will consider is, we call it trace of IQ theory, but today we are going to talk just about the tree-level. So you can think about it as a bi-adjoint theory. It's the same theory as bi-adjoint theory, which means that if you want to compute an n-point amplitude, you have to consider a disk with n marked points and draw all the possible Feynman diagrams which have external legs on the boundaries of the disk. So something like this. Well, it has to be cubic. Could have done something simpler, I guess. Okay, so this is one diagram, and you sum over all of them. Yeah, I don't know why I've done such a complicated example. Let me do a more manageable one. Let's say at 5 points. What I wanted to show you is that every diagram is dual to a triangulation of the disk. So this is the diagram, and this is the corresponding triangulation. So if we label the marked points 1, 3, 4, 5, every propagator is going to be dual to a chord that connects 2 of the marked points. Very good. So how do the amplitude in this theory look like? The simplest one, the 3-point amplitude, well, there is a single diagram in a sense. So the amplitude is just going to be, let's say, 1. At 4 points, we now have 2 diagrams. And well, usually we say that they contribute with S and T. It's going to be convenient for us to use the same labeling of the propagators as given by the dual n-gon. So I'm going to say that this is x13. So this contributes with 1 over x13, and this contributes with 1 over x24. So these are the 2 diagrams which are dual to either this triangulation, 1, 2, 3, 4, or to that triangulation. Okay, and what I mean by x13 is the propagator that is dual to this n-gon, sorry, to this chord. And in general, it's going to be given in terms of the external momenta by pi plus 1 plus ... until j minus 1 squared. Okay, so this was the 4-point. The 5-point was supposed to draw it here. Apologies. Well, we have again that diagram over there. So this is going to give us 1 over x13 times 1 over x14. And then you have 5 other diagrams which are obtained by cyclically rotating the triangulation. That's cyclical. Okay. So what are the geometries that goes together with them? At 3-point, we have nothing for the amplitude, and accordingly, we will have nothing for the geometry. It's just a point. At 4-point, we have to have 2 singularities, x13 and x24. Recall that singularities have boundaries, so we have to have 2 boundaries. Simplest thing possible is to have a segment. And at 5 points, now we want to be able to reach 2 boundaries. So we can set x13 to 0, and then we can set x14 to 0. So we want something that has to be 2-dimensional and has to have a total of 5 boundaries. So that's a pentagon. This could be x13, x14, x24, x25, and x35. Okay, and now I'm going to draw for you the 6-dimensional example, the 3-dimensional example. This is going to be the highlight of the talk. So please get excited. Okay, it works. Okay, and now let's look at this guy for a second. This is the amplitude at 6 point. We see that we have a bunch of pentagons. Why we have a pentagon? Because the 6 point amplitude can factorize into a 3 point amplitude, which is a point, times a 5 point amplitude. Total of 6 external particles. And the 5 point amplitude was given by this pentagon. So we have to find among the boundaries pentagons. But then we also have squares, because a 6 point amplitude can also factorize into a 4 point times a 4 point amplitude. And a 4 point was a segment times a segment is a square. And I'll leave it to you to understand why we have 6 of them. Okay, so this went a little bit faster. I'm getting better and better at drawing it, so maybe it's easy to miss the point. And is that it's very, very remarkable that you can actually form a polytope out of these possible singularities. If you think about it, you could have started from a singularity and put a pentagon there and try to put everything else, but there was no guarantee that in the end the picture would close and form a polytope and not something with holes. Okay, but these are very nice pictures, but now we have to understand how to get some physical quantity out of it. And the connection between a geometry and an actual amplitude comes through what is called a canonical form of the positive geometry. So given a positive geometry, there is an associated differential form that lives in whatever space the geometry lives in, and which is uniquely defined and fixed by requiring it to have a singularity only at the boundary. Well, for every boundary of the positive geometry, it has to have a simple pole. So if the boundary happens at, let's say, y equals 0, the differential form has to look like this. So omega has to look like that. If y equals 0 belongs to the boundary of the positive geometry. And furthermore, the residue at every boundary component of your positive geometry. So we see that it has a simple pole, but then there is something else. That something else is the residue. And it has to be the canonical form that you attach to the boundary itself. So this is a recursive definition that starts from some high dimension, goes down in dimension until you find the maximal codimension, dimension 0 loci points. And you require that the canonical form, sorry, here there is a plus or minus. You require the canonical form of a single point to be either plus or minus 1. Okay. So in general, it's very difficult to compute a canonical form. So let's look at some simple examples for the simplest geometries, which are polytopes. So the case where the positive geometry is defined by the positivity of some linear function. All the points y, such that some linear function is non-negative there. So the simplest example again would be a segment. So let's say that we have a segment with vertices at A and B. What is the canonical form? Well, it has to have a pole at A and it has to have a pole at B. So it could be something like this. But then recall that we want the residue at points to be either plus or minus 1, so you need that normalization factor there. And now it satisfies the requirements. Okay, this looks very simple. So we could imagine that maybe the next to simplest example, which would be something two-dimensional, something like the pentagon we were looking before. It could also be as simple as, let's say that it lives in some space projective variables. Y, this is a canonical form, is a canonical measure that you attach to a projective space. If you don't know what it is, it's not really super important. Let's say that the boundaries corresponds to some hyperplane. given by a linear equation, then you could wonder whether this is the right result. After all, you want to have it 5 poles at the 5 possible boundaries. But now this doesn't work. You cannot engineer a simple numerical factor that doesn't depend on the y's, because you see this form has a pole here and it has a pole there. So in this point here, where the planes meet, the canonical form has a pole. Sorry, if I said that cannot depend on the y's, I said something wrong. I meant that you cannot simply put a constant here. Like in this case, the numerator didn't depend on x. Here you have to have something that actually depends on y. Cannot be just cannot depend on the w's. Excellent. So the root of the problem, as we were saying, are these 5 points. The form has a pole there, and you shouldn't have a pole there because those 5 points are not on the boundary of the positive geometry. But you can do something. You can take the unique quadratic that goes there, and you can put it in the numerator. So this puts a 0 there, and it cancels the pole from the denominator. And now this is okay. Okay, this was just to show you that you see many things look very simple when you write them down, but when you try to do example, you see that these are actually very intricate objects to compute. Luckily, there is a systematic way to compute the canonical form of any positive geometry. The most important method is that whenever you have a positive geometry, if you decompose it into other positive geometries, this doesn't really require the positive geometry to be linear. You have that the canonical form of the positive geometry is the sum of the canonical form of the canonical forms of the simpler pieces. Very good. So this is a formula that we will see in action in a second. Okay. Now let's recap a little bit what we said so far. We have yes. This one. Okay, this is just we're working in projective in homogeneous coordinates. So this is in P2. So you have homogeneous coordinate y0, y1, y2. This measure is defined if you want. Okay, you have homogeneous coordinate, and then you have affine coordinates xi being y1 over y0, and well, that's it. This form is just the pullback of dx1, dx2 under this map. So you substitute x is the ratio of the y's there, and you find what it is. It's called the Euler form. It's a standard measure that you have on a projected space. The idea, it's important because if you want to build a differential form which is well defined on a projected space, you just multiply it with a function which is of degree, well, sorry, with an homogeneous function which such that the overall weight of this is 0. So for instance, here we have, if you scale y by lambda, you get lambda cube, lambda squared gives you lambda to the 5th, and downstairs you have 5 y's, so you get lambda to the 5th. So this is well defined. Yes.
It seems to me like in that example, the only possible ambiguity is another one minus sign. Maybe.
In this example, yes. Yeah, there is always an overall minus sign.
Okay, and that the only thing here? Or...
Well, if there are certain technical requirements, I can tell you more about it later, but yes, it's the only thing. Okay, so just to recap a little bit, we have seen that we have a theory where, at least in a few examples, we have seen that there are corresponding polytopes, meaning that they have the same combinatorics as the singularities of that theory. We know how to, well, we know that to a polytope is associated a canonical form, and now we will see how the canonical form of certain polytopes, or those that I was drawing before, give you the amplitude of that theory. But first, now I have to tell you how to actually get those polytopes and not just the pictures. So, how much time do I have left?
We have about 10 minutes.
Perfect. Okay. So recall that the simplest polytope was just a segment, which was supposed to have a boundary at x1 corresponding to x13 and a boundary corresponding to x24. So how do you get a segment with two boundaries? You can simply look at the positive region where one of these functions is positive. Sorry, where all of these functions are positive. And intersect it with a plane which guarantees that they cannot go to 0 simultaneously. So if x13 is 0, it cannot be that also x24 is 0. So why do we get a segment? Why do we get that segment? Because the positive region looks like this. And now we intersect it with a plane. So we get this segment here. Okay, this is the basic idea that creates all of these polytopes. I should mention that these are called this is the ABHY realization of the Associahedron, which is the name of this polytope. Arkaniamed, Yuntabai, Songe, and Grassmannian. Okay. So in general, we're going to build a nice triangle where we record all the possible chord of the angle. Recall that the chord of an angle corresponds to the singularities of an amplitude in this theory. So for instance, we could have x13 and x14. And now we build this mesh where every time you move in this direction, you increase the second index. Every time you move in that direction, you increase the first index. So here you would have x23. If you recall the picture that I was drawing before, x23 is a boundary chord of the angle, so it doesn't really correspond to a propagator. It's dual to an external leg. So this quantity is supposed to be 0. So x23, x24, x25, and x35. Here we would have x15, which is also 0, and x34, which is also 0. So at the boundaries here, we only have 0, and the 5 possible propagator live here. Now, for every mesh, for every little square that you have in this picture, you impose an equation like this one, which keep apart two incompatible boundaries. Whenever you have something like this, you write xij plus xi plus 1 j plus 1 minus left and minus right is equal to a constant. So for instance, in this case, we would have x14 plus x25 minus x24. We would have minus x15, but this happened to be 0. So you ask this to be some positive constant. Let's call it C14, using the same label as the bottom corner. This is we ask this positive number, this constant to be a positive number. So this means that the variable x14 and x25 cannot go to 0 simultaneously if x24 has to be positive as well. And if we go back to the picture of the angle, 1, 4, and 2, 5, 1, 2, 3, 4, and 5 correspond to crossing chords. Crossing chords obviously cannot be dual to propagators that appear on some diagram, because a Feynman diagram is dual to a triangulation, and a triangulation is built out of non-crossing chords. So we don't want these boundaries to meet. These are incompatible singularities, and this equation guarantees that this doesn't happen. Okay. Now, this is going to be very hand-waved. I'm not going to prove that this actually gives a realization of the polytope that I was drawing before, but this just gives you the idea. Now, finally, we're going to compute the first amplitude of this talk. We're going to compute the 4-point amplitude. So attached to this polytope here. Well, we could solve this constraint by saying that x24 is equal to c minus x13. So I'm going to redraw the polytope as having a boundary at x13 equals 0. So this is the space x13. And another boundary at x13 equal c, which corresponds to, on this point, x24, which is equal to c minus x13 is 0. So before we wrote down the formula for the canonical form of such a segment, it was b minus a, so in this case it's just c over x13. And then we have to put the other boundary, so c minus x13. It's a differential form, so it's multiplied by the x13. So fine. So this is the canonical form, and the claim is that if you take the canonical form and you divide by the measure, so you strip away that factor, the function that you're left with is the scattering amplitude. And it is, because this is just the same as 1 over x13 plus 1 over x24. Recall that x24 is given by that. Okay, so a lot of work to get the usual representation for the amplitude, but now let's look at a juicier example, the 5-point polytope. So, and we're going to find a new formula that doesn't look like a sum over Feynman diagrams. So if we write down the equation corresponding to these guys, let me do it, it's very quick. x13 plus x24 minus x14 equals c13 greater than 0. And x24 plus x35 minus x25 equal to c24. So you can solve this equation and express all the x's but x13 and x14 as a function of x13 and x14. And you plot the region where the corresponding function are positive, and you find the following polytope. So let me do it a little bit better. Okay, so this lives in the x13, x14 space. This is the boundary where x13 is 0. This is the boundary where x14 is 0. And you will find that this is the boundary where x24 is 0, x25 is 0, and x35 is 0. So you see that, for instance, the boundary x13 and x24, they do not meet on the polytope. You have to actually do it to see it, but it's a very simple thing to do. Now let's compute the canonical form of this object by doing some decomposition. So for instance, the particular shape of the polytope suggests to take this decomposition. So we divide the polytope in P1 and P2. And the reason why we do that is because each of these pieces look very simple. It's what is called a prism, meaning that it has a bottom facet and an upper facet, which have the same shape. So you can imagine that the canonical form of this guy is going to be the product of the canonical form of one facet times something that puts a pole at the bottom and at the upper facet. So for instance, for P25, the 5-point, omega of P2 is going to have a pole at x13 equals 0, a pole at x25 equals 0. And then here we need the canonical form of the facet at x25 equals 0. But because everything is completely recursive, the canonical form, this facet is a polytope associated to a 4-point amplitude. We have computed the 4-point canonical form here. So the canonical form of this facet is going to be essentially this after you relabel the variables. So this is going to be 1 over x35 plus, here there is a little surprise because this was a form living in a one-dimensional space. Now you think of this form as living on a subspace of a two-dimensional space. And when you do the pullback to promote it to a form on a full dimensional space, you find a slight deformation of that formula. You find instead of having x24, which would put the pole just here, you find x24 minus x25, which puts a pole on all this internal boundary. So you find this formula. For the other piece, omega p1, you find x13 plus x24, 1 over x14 plus x25 minus x24. Now, the amplitude is the sum of these two pieces. So these are functions, so maybe I call them like this. And now this doesn't look like a sum over Feynman diagram for a very simple reason, that you have introduced a spurious pole at x24 equal x25. And of course, if you sum over Feynman diagrams, you never introduce, by definition, almost as poor as possible. So here you would find the 4 terms from one side, from another side, and there is a cancellation that makes sure that the formula collapses to the usual 5-point representation of the amplitude. Very good. So how much do I have left? I don't have any time left. Good, because I'm done. Well, no, I wasn't done, but I am done. Maybe I will just tell you something real quick about the conclusion. Almost done. Here it is. Was the last page. I just wanted to tell you that all the things I said so far is in this simple case of a 3-level planar amplitude, but actually generalizes to every order of the 1/n expansion in this theory. So it doesn't rely on the planar, on computing just the planar limit as in the usual n equal 4 Superganiel's case. And also you find a recursive formula for integrants, but you can also compute the loop integral and find interesting formula for an actual amplitude. And now I'm done.
Thank you very much, Giulio. That was really great. Shorty has a question.
I was just going to ask if there's a version of this.
Yes, there is. So there are many versions. I think Pinaki Banerjee was one of the first to do something about it. There is actually a version that Nima was telling me about. Nima was telling me about many things. It's a shame that it's not here, which actually is able to write down any phi to the p interaction, even mixed interaction, using this story. So from the polytope of phi to the cube theory. And then there is also, well, but there was another question.
Yeah, you said something about the bootstrap again. I wanted to understand that does this produce integrals?
Yes. So to be more precise, what it produces for you is so you know that for a single Feynman integral there is a Feynman parametrization, right? So there is no loop in that expression. Of course, there is the parametric integral to be done. What this gives for you is a unique integral over a space. In a sense, the space is the dual of this polytope of an integrand which is piecewise linear on this space and is not defined by summing over the Feynman diagrams. So if you want to evaluate this integrand on a point of the integration space, you don't have to write on your computer a code that generates all the Feynman diagrams and computes a value for that particular point. It does so in a way that scales with the number of singularities of the amplitude rather than with the number of Feynman diagrams. But then you do this integral, you can do it in many ways. You can do it in Monte Carlo, for instance, and you get an amplitude, literally a number which is the amplitude.
Would it be fair to say that you get a novel type of Feynman parameterization, however unusual one, and one that's valid for the full amplitude? Right?
Indeed, yes. The best way to say is, as Janis just said, it's a global Schwinger parameterization of the amplitude. Sorry? Actually, in D dimension. Now, the thing is that, of course, in general, there will be divergences. So you can compute a globally parameterized, dimensionally regularized amplitude, or you can do it in 2 dimensions, where actually there are no divergences if you exclude surfaces. I didn't say the word surface before, but for every surface, there is an accompanying polytope. If you exclude surfaces which have punctures in the bulk, if you only allow punctures on the boundary, dually, this gives you diagram without tadpole. This gives you tadpole, so if you don't use these ones, if you ask to only have market points on the boundary, the dual diagrams are convergent in 2 dimensions. So you can compute in that dimension, and it gives you a number. Yes.
All plus amplitudes.
All plus, but this is a scalar theory. There is no helicity here. This is a literally phi cube theory.
But I think the claim is that you use d-dimensional integrands. So of course there remains a question of renormalization and so on, but it's not only an integer dimensional
yes
outcome.
And I mean, we're not completely crazy. The reason why we care about this theory, about trace of phi cube theory, is because it's the theory that asks you to sum over all diagrams that you can draw on a surface. Right? Yang-Mills, in a sense, is also a theory like that. The difference between Yang-Mills and trace of a cube theory is that you have to add interesting numerators. How to treat those numerators in this language that we don't understand yet. But we're optimistic.
Yesterday, he was talking very briefly mentioned that this picture there's maybe some way of trying to consider going beyond the cosmological polytope story that happened a few years ago.
I was also very curious about that comment.
Any final questions? I think it's really, I want to thank especially you, Julia, that you agreed to give this talk on very short notice. I think it was very
My
clear.
pleasure.
And, thank you for it.
Thank you very much.
So likewise, what I just said also goes for the next speaker, who even more than being requested on short notice was even given some wishes for what a possible topic could be.
Well, I couldn't obey the requirement put by organizers.
So do I assume correctly that you will tell us something about infrared divergences in the context of scattering amplitudes and cosmology?
Yeah.
It's wonderful.
So, yes, thank you very much.
So Fisher, please take it away.
So thank you very much. So as Johannes advertised, so I'm going to talk about infrared division. And actually what I'm trying to tell you some story which mostly will take place on the amplitude side. But actually during the workshop, I learned a lot of new things about cosmology side, and I believe, I hope, these lessons which we learned about gauge theory will be helpful for cosmology as well. And you should forgive me if I will tell you some notes about cosmology side, because once again, I'm just in the process of learning, and thanks to excellent power lectures and some nice seminars we had during the beginning of the week, I think I understood something. And let me start kind of summarizing what we have heard at the beginning of this week. So I'm going to talk about cosmological correlators, and you have seen already a bunch of diagrams appearing. For example, the diagram which appeared in our lecture, it was that one. So you're talking about production of particles out of particular vacuum. The case of the city, it was Bunch Davis vacuum, but in general, from what I understood, you could formulate the problem in general terms. That is the cosmology, you have some curved background, and you look for the production of particles out of this curved background, which is detected at certain time. And here you have particles which enumerate 3 and 4. And then, so this object goes under the name of cosmological correlators. And then what you have seen in Powell lecture and also yesterday in Nico's talk, that if you look for the properties of these correlators as a function of the energies of the particle produced, it has certain analytical properties. One particular lesson which I learned, so that if you look for singularities, for example, of the total energy of the system, you will find that in general it will behave as a total energy in some power. And what appears here in the numerator turned out to be on shell 4 particle amplitude. So in this case, it will be 4 particle amplitude, it will look like that. And in this way, for me, this relation which kind of connects to different worlds, the world of cosmological correlators and the world of the scattering amplitude. And yesterday, during Canonical talk, he actually mentioned that there is kind of one-to-one corresponding with different observable we could define on both sides, cosmology side and the gauge theory side. One of them was so-called in-out matrix element, which were exactly scattering amplitude. And then there was so-called in observable on the cosmology sides, which were corresponding to total cross sections. So my goal would be kind of to tell you what happens on the left-hand side or on the right-hand side of this correspondence. And hopefully by the end of my talk, I will try to go back and tell you something about what happens here if you start going beyond tree-level approximation. What I mean by tree-level approximation, I really want to talk about those cosmological calculators, by going deeply into loop level and trying to see what kind of structure you're expecting to find on the level of the loop. And I wouldn't answer that question, but I will answer the question what will happen if you start looking for analytical properties, namely what happened here in the middle. And hopefully by the end of my seminar, you will see the answer of what's going here. It's very simple. So, but let me start slowly. And as I told you, I will start from gauge theory side, and the natural things to consider, which follows analogy with the process you have over here, is a process which goes under the name of the E plus E minus annihilation integrand. So let's talk about this particular process. And the reason to show this process is actually twofold. On one hand side, one of the most best studied processes in PhD, and we know a lot of things about the process. And second reason is that if you actually look how this process looks like, you will see there is very direct analogy between what happens here and what's going to happen over here. So namely, you start from a flat space, everything is stable, nothing happens, no particle production. And now you want kind of to create something that you have here, but instead of putting the curved space, I excite my vacuum by certain operator, or if you wish, by producing some virtual photon, have E plus minus annihilation, virtual photon, and in physical terms, it corresponds to situation when you excite vacuum by applying electromagnetic current with certain energy or momentum. And this energy gets released, and it released to produce your final states. And in this particular picture, the final states will be paired quark and antiquark. You start moving apart, producing a lot of radiation. For example, each of them could emit a gluon. And in this case, what you're going to have for this particular diagram, you have production out of the vacuum for particles. And those four particles are exactly similar to particles you have over here. So in this case, you have one-to-one analogy between production of particle in the super space and production of particle in the flat space out of the vacuum. And because of this relation, you're expecting there will be some kind of crosstalk between the different pictures. So now let's go a bit deeper into this object and try to see how you could actually compute this object. So there is two ways to compute this total cross-section. One way goes through this formalism in our formulas, or another way of saying you could decompose total cross-section into the sum of the final states. Let's call X all possible states which you produce it. And in this way, the total cross-section will be sum of the total final states, and each final state will contribute to the matrix element of the transition of the initial state virtual photon to the final state. And in this particular case, if you just start thinking about developing equilibrium expansion, so this becomes form level diagram, initial photon goes into the pair 4, then you will get the diagram which corresponds to emission of one gluon, etc., etc., etc. So then you take modulo square, you integrate the phase space, and you will get what you will get. And let me mention that there is another diagram which will be important in what follows, which corresponds to the virtual exchange. So these are kind of classical textbook. So this was way number one, which goes to the amplitude. But there is much more efficient way, which also was mentioned yesterday in the talk, which goes on the name of the optical theorem. The optical theorem tells you that the total cross-section is equal to the imaginary part of a forward scattering amplitude. In other words, instead of going through the amplitude, let me consider the particular process when you have virtual photon goes into everything and goes back into itself. And then I would like to compute this object. And this object, I mean, time-ordered correlation function of two currents. Let's put the point x0 instead of point 0. You take this correlation function, you evaluate it deeply in Euclidean space. So there's no divergences, everything is finite. You take Fourier transform. You get function of Q. Then you do analytical continuation from negative Q square to positive Q square. You take its imaginary part with Levy continuity on the top. And this object by optical theorem will be exactly the same total cross-section we have over here. So if you do calculation second way, you'll get perfectly finite number. And actually, this total cross-section in PDD, it has the following form. So the sigma naught corresponds to the bone cross-section. There's nothing happens here. Then you include one gluon here. You do the calculation. You will find the famous result that the one loop cross-section is proportional to alpha s, strong coupling constant, divided by pi. And it could continue so far and so on. And I believe by now you know analytical expression for the cross-section up to for loops. So this is just another way to tell you that this second approach is quite efficient to go loop by loop, doing calculations without encountering any problems and any step between calculations for dimensions. There is no even point to talk about doing any regularization whatsoever. Just perfectly fine calculation which you're doing for CD order by computing correlation function. But now let's go to the first approach and try to see how could we reconstruct the same number that goes through the amplitude. And at that moment, you immediately run into trouble, and the trouble arises due to infrared divergence. So how do we see this divergence appear? So let me start from the last diagram. Let me turn it a little bit, like that. And once again, we're talking about diagram. We have two particles produced, two quarks, and then you have some virtual gluon emitted. And obviously, contribution of this diagram will be proportional to the power of coupling constant, and the integral of the phase space the virtual gluon. And then let me be a little bit schematic. I won't put you full numerator. I just keep only one with 10, which will be relevant for discussion. So these are approximately equal. And then, as you know very well, what happened next is now we take into account that P1 and P2 on its mass shell, we take quark massless. You could simplify this expression a little bit. And now you see the problem here. So the problem is that if you start computing this integral, you immediately realize that it's ill-defined. So that is the reason why I put here, and let's take d4 minus epsilon. The problem is here from two potential dangerous regions. The first is the region when k is small. So when momenta k is small, all components are small. This same k square obviously will be subleading compared to the leading term, and then you will see 4 powers of k in the denominator, 4 powers in the numerator. These are signals you have divergence, and since divergence come from small k, there's definitely infrared divergence. So this immediately will give you a false. Is a parameter of epsilon parameter regularization. But this is not as the story, because if you look once again at this integral, you will see that there is yet another divergent region will come if k is not small, but if it's aligned with P1. Since P1 is like vector, you immediately see that when k is aligned with P1, this denominator vanishes, it vanishes as well. And this is sufficient to produce a divergence. And similarly, if k is collinear to P2, you will get yet another contribution. In total, it will be double pole. What does it mean? It means that you start from a very simple diagram at lowest order perturbative expansion, and you already see that at that level, you're bound to introduce dimensional regularization. And at the end of the day, you get divergence, which is double pole, one pole because of the infrared, and second because of the collinear. So these are synonymous of saying that as soon as you have massless particles propagating in your series, you should be expecting to get into troubles, and these troubles, in this particular case, appear as a double pole. But now, if we come back to the first slide, we immediately run into this problem because we got two diagrams at one loop level. You know, the sum of them have to be finite because I already gave the answer, but that one is divergent. So the way how everything should be finite is diagram with divergent as well. And indeed, it's divergent because the computing contribution of this diagram is emitted gluon. What you have to do, you have to repeat the same calculation, but this time you have to take this diagram, take it modulo square, and this case you're dealing with emitted gluon k. This will slightly modify your integrand. It will become now delta plus k squared 2 pi, plus refers to the fact that the gluon is outgoing, its energy is positive. And then it could perform similar analysis to realize that this integral is also divergent. G squared 1 over 1 square. with some sign. And if you could guess that if you now add together this distribution of division with that one, this division, that then you get something finite, and then you could reconstruct the final expression, which will match exactly the one which was coming from QCD calculation. So this way, from this simple exercise, what you see is that if you do calculations to the amplitude, you will start dealing with infinite divergences. You will have to introduce dimensional regularization intermediate steps, but the final result is perfectly finite, and it matches the result of the calculation of the correlation function, which was done entirely in 4 dimensions. That's another way of saying that if you're always dealing with so-called inclusive quantities, which total cross sections, they're much better suited to doing calculation, because basically you don't have to deal with those infinite divergences which I described you previously. So the next step is to understand what's the physics behind those divergences. Why do they appear? What will be the general rule? In which situation you expect them to appear? And the answer to this question has been given a long time ago by Lee Naubert and Nishida. Lee Naubert and Nishida. I really forgot which year, but it was a long time ago. And what they found quite interesting things. Namely, what they're saying is that if you're thinking about the diagram, and we agreed that the divergence comes from situation when K is soft, or K is collinear to either P1 and P2, in physical term, this corresponds to a very special situation when your finite state becomes degenerate. What do I mean by this? So imagine you want to define this object as matrix element between virtual photon states, and in this case, it will be state of the quark, anti-quark, and the gluon. If you're thinking about state of the quark, you will specify the state by giving its four momenta and its quantum numbers. But now what will happen if I will secretly add to this quark some gluon with zero energy? Since the energy is zero, these particles are unobservable. But if you're thinking about quark and quark with gluon with zero energy, from a point of view of quantum numbers, it's the same state. So therefore, strictly speaking, if you go to the limit when K is soft, particle is soft, you have degeneracy between single particle states, quark, and quark with the gluon no matter going to zero. In the same manner, if you now go to the collinear limit, if this gluon is aligned with the quark, you have exactly the same situation. If you have two particles which align, you can distinguish by any experiment one particle from two particles which have the same linear momentum. So this is actually the situation we have degeneracy of the final state. And the statement of this gentleman, is to say that every time you have degeneracy at the level of physical states, you bound to enter these troubles. And another way to see it, you don't need to go to quantum field theory. It's actually, this phenomenon is known in quantum mechanics. If you are doing a bit of expression in quantum mechanics, this problem is known as a problem of small denominator. Just let me give you some flavor how it appears. So imagine you have some quantum mechanical system. We describe a certain Hamiltonian, and you want to find eigenvalues and eigenstates of this system. You could think about this Hamiltonian like describing the asymptotic states in your theory. Please?
When you say these are degenerate states, are you assuming that it can be charged?
If you have a quark has color charge, a special electric charge. But now if you have quark with certain quantum numbers, you name it, energy, momentum, electric charge, etc., what I'm saying is that if you're now adding some gluon which goes same momentum, is momentum which lies to that quark. There is no way you could distinguish this state from that one if they have the same global charge.
Oh, I thought you were saying that the initial state would become, that it was a degeneracy.
This is exactly what I'm saying, is that if you're thinking about these amplitudes, you have initial particles momentum P1, and another, let's say, P1 minus alpha K, and here's alpha K. So you have initial state, which was quark, single particle state quark, which has momentum P1, which is like. And now I'm looking for the final stage, which now consists of the quarks and gluons. And I'm taking momentum of quark to be P1 minus alpha K and gluon being alpha K. And now what I'm saying is that this K, I could choose to be aligned along P1 direction. So I have two particles which move in the same direction. Then these states and coming and going states have exactly the same quantum numbers.
Okay, so you're saying that you should add up the real radiation.
Is that exactly? These are what come up with the recipe at the end. But the reason why divergence appear, the underlying reason why divergence appear in this case, is because of the degeneracy of this state together with that one. For example, imagine if quark, or for example, if gluon had a mass. If gluon had a mass, there is no way you could have particles massless particles split into massless particle and massless particles. Such amplitude does not exist. It's contradictory with energy matter conservation. It's only particle with a massless this could be possible. It's because they are massless you generate divergences. But once again, the reason, the starting reason is exactly because of the degeneracy between initial and final state. And just to give you a explanation for this, actually, you kind of already seen this in quantum. Please?
The final state and the state right in first state.
Again?
Not the initial.
Okay. Well, let's. I see. So imagine you have in general situation. Imagine you have static and have n to m particles. So I have n to m particles. And now I'm saying what will happen if I add here one additional particle to the final state.
Yeah.
So now if you go to situation we have here, it corresponds to the situation when you have the same initial state, but this final state with and without particles are degenerate.
But those are not the only divergences.
It's only mean
In the forward region,
in which region?
and like in the Glover region.
If you're talking about globular region, it corresponds to the exchange in the it's called initial state interaction. When you have a change on the gluon, and this gluon will have mostly transverse momenta, but its transverse momenta much smaller than the momentum of m particles. Therefore, in the limit when energy of the particles goes to infinity, it's the exact situation we're talking about. So all divergences, infrared divergences, collinear divergences, Glauber divergences is exactly the same mechanism of the degeneracy of the space. And let me just finish with one mechanical exercise. This probably, hopefully, it will be very clear and clear. That imagine you have some kind of mechanical system, and you want to look for solution to the system, and you know that this Hamiltonian H describe your free particles with some interaction. The interaction comes with some coupling constant time c. So you're looking for trying to kind of perturbative solution to the system, looking at perturbation powers of the G. So then, as usual, what you do, you start regulating your free Hamiltonian. And in physical terms, this free Hamiltonian will give you the spectrum of particles. And now you're asking the question, what will happen if I turn on the interaction? How this wave function will change? How the energy will change? Okay, then you look for perturbation theory solution. You will find the energy of the state delta E. You get the correction, which is expectation value of the perturbation. But if you look for the change in the wave function, it will be more complicated. It will be infinite sum, so all states will contribute. So you start from one particular state, and you perturb it slightly by the interaction. And you ask the question, what will be transition amplitude from the new states to the original one? So these are new states will be given by the sum of all states. This is kind of the perturbation. And now you look at that expression, you need to see there is denominator. And this denominator tells you how your states, which you're talking about, different compared to other states. And this is exactly what I was saying, that if it happens at situations that this denominator is very small, you're in the trouble. And situation we're dealing with here is exactly this situation when you have this energy M, energy K, which differ by additional ones of particles. These are all trouble stuff. So once again, divergence is collinear divergence is synonymous of having these degeneracies in the final states. And once again, this gentleman leaving now with Kinoshita, they also gave you a prescription how you could get rid from this problem small denominator, or another way how you could get some physical, final physical observables using divergent amplitudes. And as you know very well, there is a very defined prescription which goes under the name of summation of the final initial state. If you include enough, if you just sum all final states, for example, in this situation, a virtual photon going in arbitrary number of particles, if you're sufficiently inclusive with respect to final state, this theorem will tell you the final result will be finite. And indeed, it's finite, as I told you, that at the end of the day, you will reproduce total cross-section, which comes from CD calculation. So how does this model later gets resolved the knowledge here? So you start from this point. You have your theory, no interaction, free particles. You're defining your Hilbert space. The Hilbert space will consist of 1 particles, 2 particles, 3 particles, any number of particles. Each particle comes with its own momentum. Then you think, what will be the transition amplitude? Like the picture which I arranged before. You're saying I have transition like that, and I look for my initial states, which are called here psi m, go into some final states, which are called psi k, and inside this block, you have this interaction V, which here over here. So then, if you apply that formula, you will have to sum over all possible states, which appear in this formula, and the denominator will come with a difference between initial and final state. Now, what I'm saying that if you now have particular final state, so you have chosen final state. Now, if you give some additional particle, this additional particle would contribute to the sum with yet another contribution with 1 particle more, and then it will also contribute over here. And what I'm saying is that now, if you have a situation where n, this states n and this states k differ by some small amount, the small amount will be due to emission of this soft gluon. You will have here 0 in denominator, and this 0 will create the divergences.
So that's great, but I also have a similar question. So I see that there is a divergence, but you're saying that if I sum over all possible finite states, the divergence is going to cancel out.
Yes.
Is there some intuition of what is the zero that cancels this? How does it cancel out? Do you have an intuition of this level?
Well, so this gentleman was saying, so if you start from this object here, and now you want to look for the total cross section. So this then it will be Scalar. If you project this sum in particular states with the transition matrix element between the initial state and states k. So forget about the sum. So you have the denominator times the matrix element. To get total cross section, you have to take a modular square of this object and sum of all final states. In this case, you will have a double sum. Amplitude has this denominator. You take its modular square and you sum. Then what they're saying that if you will sum over all final states over k, and also over all initial states over all n, there is some simple manipulation with the sum will tell you that at the end of the day you will get 0.
I think of this cancellation as being 1 over en minus ek plus 1 over ek minus en.
Something like that. Something like this. These are more or less what will happen if you sum over both initial and final states.
One
But-
actually doesn't need to sum over
we-
both. Just
I come to this. But the initial theorem due to linear Alberti-Nishita requires you to perform summation of both initial and final states.
right, but it's just based on unitarity, so 1 minus 1.
Okay, but then exactly what you're saying is that in my example gave you before, I started from the initial states, which there was no particles, which you have in the final states. It was kind of initial states was kind of coming from external virtual photon, and basically optical theorem told you that the final result will be finite. These are what called Bloch-Nortzig theorem, which goes atop of linear, saying that if you're dealing with a cross section in the initial state doesn't contain particles, which could potentially produce divergences, then there is no need to sum over initial state. It's sufficient to sum of the final.
It's also true that you
Yes. Okay, right. But if you have at least 1 particle in the initial state, which could potentially emit those soft linear particles,
doesn't
then
matter.
no. Then you run into problem with divergences.
Uh,
But those divergences are called.
For example, Compton's there at tree level,
Yes.
and that's divergent, and that's and there's nothing that can cancel the divergence to be finite.
Again.
If you take Compton's there
Yes.
at tree level, then you see that we have to include the forger by unitarity.
So let's be more precise. Let's be more precise. So let's talk about exactly what you said.
Yeah.
But I will take slightly more different process. I take deeply virtual quantum scattering. I want to scatter virtual quantum of my core. Okay? I look for this process. This process goes under the name of deeply nice scattering. Deep nice scattering, if you compute, for example, the diagram over here, you will find that it contains both infrared and collinear division. However, if you sum up this diagram with all other, for example, the watch includes here enrichment correction, you will find that double pole will go away, but simple pole will remain.
Yeah.
So therefore, in this situation, once you have initial states which could emit of particles, there is no oscillation of the poles. They will still have division.
Forward scattering.
Again,
If you include the forward scattering diagram. So by the optical
Yes,
theory
yes.
of m minus m star equals 700 kilograms.
it will division.
Huh?
It will be
Each,
division.
each one is divergent, but if you sum over all of them,
No,
that's
no, no,
that's
it's not true. This example, these are forward scattering, so I have initial and final state being the same. So you take imaginary part, it becomes total cross section, and total cross section in the case when the quark is matters is infinite. It has simple pole, and this simple pole. So, but then what's the question?
But no, my question is, or my statement is just that if we want to cancel this divergence.
Yes.
You know, for example,
Yes.
there's a compass scattering last 3D at true level, this period, we get a divergence.
Yes.
And the only thing that cancels it is forward scattering there. Where you have E plus E minus photon to E minus photon like box diagram, which is like the left-hand side of the optical.
This is contradictory to what people have been doing in CD for last 40
I
years.
know. But there-
Because let me first state what people know in QCD, and then probably will come to what is. In QCD, this part becomes part of the yet another formula, which called on the name of the Gribov-Parelli-Parisi evolution equation. So this diagram tells you that you have quark, which is massless quark, which carries certain momentum. This diagram will appear as a part of the full physical cross-section. The physical cross-section is corresponding to the incoming photon. And the final contribution becomes integral of the issue of the momentum carried by this quark. It's become some scaling variable called Z times the diagram which we are talking about, which goes under the name of the quark distribution inside the photon, which depends on the mu, because mu is exactly this cutoff regardless of divergences, times this process which we computed. So this C it exactly goes into this process over here, and it also contains Q squared. So this diagram which I told you, according to the standard procedure law, contains simple pole. Yes,
That's basically.
yes,
Yeah,
but it's fine.
yeah. First.
No, but that,
I was just making the statement that if we want to use scaling here to cancel divergences, then that's really, the proof is really just unitarity. So if we want to figure out which diagrams cancel, then we have to take, basically it relies on, if we want the total cross-section planet,
yes.
then we need the forward scattering diagram.
Okay, I have slightly different understanding of linear Recursive theorem. If you want to cancel divergences, which is the one which is depicted here, the diagram which will do the job is one where you have initial balloon. Diagram will go like that. So you have to put, so here we're talking about initial state being 4, which means go to the final state. But now if you want to cancel this diagram, you have to add to the initial state gluon, which goes together with quark. And then if you square amplitude, it also becomes the final state. And now if you integrate the phase space both gluon and quark, this diagram will cancel the. And this goes in the line which I was saying previously, that now you have to include not only some of the final state, but also some of the initial degenerate states. And in this case, the degenerate state will correspond to the gluon and the quark being the line momentum. But these are not part of our physical cross-section. That is the reason why the diagram doesn't go into the final expression, and which explains why here you have to be dependent on the square. How much time do I have? Zero.
Well, we had some great questions, which however were probably not your main topic. So I think it would be nice to hear what you had planned.
Yeah. Let me. I have 5 minutes.
Yeah.
Okay. So now, well, I hope kind of like I get you some feeling about all these problems, the divergence, theoretical linear, etc. But now the question appears. Let's come back to the question which I asked previously, namely, what we will put here in the numerator. What will appear here in the numerator? It will be certain amplitudes, let's say 4 particle amplitudes, and I want to go to include loop corrections. Basically, I want to go loop by loop and to see what will happen. So I already told you that already at one loop level, you have those virtual contribution. So you have a diagram like that. Please.
Like the head of time asking this question, but
So the analogy with cosmology should be that if I compute a very high-end correlation function, then I probably do factorially, and that is kind of the analog of having higher divergence class.
Once again,
The other kind of higher divergence that in cosmology, those are physical. So, I mean, that some of them are discussed, like log of KT, and these are real growths due to the expansion of the. But I think that this is I'm a bit lost in the analogy with the higher divergence.
once again, I'm not a cosmologist, right? But I'm telling you what I know from field theory side. And in this correspondence, first of all, you realize that the logic we're talking about doesn't strictly correspond to the observable quantities. What appears here in the numerator will appear after logical combination of what you observe to physical region with respect to the energy. And only if to do such kind of combination, you will count the static amplitude, short static amplitude. From that point of view, there is no contradiction with what you're saying in the object which I'm dealing with. But in general, if you're thinking about the source of divergences, from point of view of amplitude person, exactly given in mind what I told you previously. So you have a diagram like that, when here the particle which you detected, they're effectively massless particles. It means that you have exactly the same situation which we have in gauge series. What I mean by this is, for example, here at some time close to observable time, you're changing by some particles, which is soft. And this particle could potentially create a problem. I don't know what kind of problem created because I never did the calculation myself. But it's what it's true. That if you now translate this diagram, which will appear here, what will stay here in the numerator, exactly because of this exchange, will contain the third division.
I think that what you're saying is sort of the condition in the absolute sense that in the quantum process there is sort of divergence that Scalar was talking about, you split the sign units, and that is not what you're taking into account. But then there are the soft divergence, but the collinear divergence are really in the physical region. You will see it just when you do the information. So in that sense, you need that probably the conservation of say in order to get the right thing when they take the space limit, but in and of itself, here with if you are at a thematic point in physical region, you won't see it because you really in order to see it within the you really need to get
But this is exactly what you're doing here.
Yeah. So it's
Once again, we agreed that the picture which you put here left-hand side which corresponds to real physical situation. It's not the one which will appear here in the numerator. There is a continuation goes from here to here. I don't know, as I promise you, I don't know the answer for the diagram here, but I do have an answer what happens here. Okay? And let me advertise the answer. That is, you will see hopefully in final amount of time. Actually, once you resum all the three divergences and you go to the limits when cutoff goes to 0, like epsilon goes to 0, here you will get 0. Which is another way of saying that if you go to the situation when you put here elastic amplitude, and here we agree that object which will be here will be amplitude with a number of external x, which is defined by another particle detected. For given number of detected particles, in the limit when cutoff goes to 0, the amplitude vanishes. All elastic amplitude vanishes.
that's for
No, for residual dipole.
Yeah,
For the amplitude. For cross section, everything is fine. Let me just elaborate on this, and I think I will finish. So now, the statement which I'm going to make is that coming back to PTD, or in general, the statement holds for any dimensional gauge theory. So if you computed, for example, any amplitude with fixed number of external x, and you choose kinematic such a way that there is no degeneracy. Let's say all these external momenta will separate in space time, or another way of saying, all Mandelstam invariants are different from 0. So these elastic amplitudes will have an infrared interlinear divergences. For example, if you're changing some soft gluons between some external x, or if you need collinear gluons connected to blue x, so it has the Frey division inside. But if you take now the Frey cutoff to 0, this amplitude will go to 0. And this is consequence of unitarity. Let me show you how it works. Let's come back to this example which I gave you before. You look at the local section of any plus or minus deletion, and then you look for amplitudes of the virtual photon. For example, you have a possibility of having no real emission, what was square, then you have a possibility of having, let's say, one particle is the final phase, etc., etc., etc. So in principle, you have here infinite sum from 0 to infinity, and each term of the sum corresponds to very special amplitudes of producing exactly n additional particles. So now let's look for the sum. So because it involves amplitude modulo square, you have infinite number of terms, each of which is positive definite. There's no question about it. The concept is optical theory. So now let's look term by term. So for that term, we have mutual emission, and we have seen previously there is divergence over here. So this object here itself involves some powers of the parameter dimensional regularization. So now what will happen if I send epsilon to 0? So there is two options, which is three options. One option, it will go to 0, another options will go to infinity, and third option it becomes constant. Let's examine this option one by another. So if this term goes to infinity, you're in trouble because you know the total physical cross-section is finite. But here you have already infinite number of terms, and you already identify the first term, which is positive definite, blows up. It's not possible. So let's examine option number one. So what will happen if it vanishes? If it vanishes, then it's perfectly fine because you have infinite number of terms, each of them is positive definite, and this way perfectly well consistent that if you take infinite number of terms, each of them is vanishing, you take 0 times infinity, you could get whatever you like, including the final result, which advertised here. And this is exactly what happens in Cosmology. And the statement is this is exactly what happens in generic H theory. As soon as you have amplitude is expansion, which develop as divergences, and they blow up in certain way when each one goes to 0, the unitarity will tell you that actually each individual term on the sum has to vanish, which is the statement which I gave here. The elastic amplitude have to vanish because of the unitarity.
So what they're saying relies on the fact that we can consider cosmology a process which involves H theory, or it's more general because
it's the same as the following. So it doesn't matter which you're talking about. So you have some observable,
yes,
which could be expanded to a number of particles produced. So first test, those particles should be massless, because if you have massive particles, there is no even issue in that way. Then you look term by term, for example, have virtual emission, long emissions, etc. And you look whether those emissions potentially could develop infrared divergences, collinear divergences. If they do, you use the same situation. It may happen they do not. And we know a lot of examples. Such series when even though particle massless, you don't have infrared divergences or the if there is no divergences produced, you in this third scenario which I mentioned previously, when amplitude is finite, and then there is no problem. You have infinite number of terms, each of them is finite, you sum them, you get finite result. But if you do encounter infrared divergences, this is exactly the situation which you will do. And so basically coming back to what I was telling, relation with cosmological correlators and those residue, as soon as object which appears here is on shell amplitude, which involves massless particles, which could potentially produce infrared divergences. But this argument, you could convince yourself that as soon as you resum all the corrections, divergences will kind of combine together. Most likely they will exponentiate, but this statement is well known in the series. So finally, to suppress them, so infrared divergences in the key text of the amplitude should suppress it, not enhancement, but suppress it. These are basically what I wanted to tell. I'm not sure how useful it is for cosmological side, but at least it's a lesson that you could learn from my experience with academics.
Thank you very much, Gesha, for this wonderful talk, and already had some inspiring discussions. We have time for questions today.
Can you explain again why wasn't the third option? Which for these terms are finite, but they get smaller and smaller and
yes.
Why is not that option?
Yeah, this is I said. Sorry, maybe I explained it wrongly. You have three options. If there, you may have a theory which contains massless particles, but still there is no different division. You know, the presence of massless particle in the spectrum does not guarantee that you will have the divergence. And then imagine you do have divergences. Another way, you start drawing diagram, and for example, let me show examples that Paolo was describing. So you have 5 cube theory, and for example, I take amplitude like that, and I'm changing Scalar particle. If you write the integral, the more the same integral which I was showing before. This diagram for massless scalars will produce your double pole. So therefore, I cannot guarantee, right? Once again, I could make a theorem statement, but for me, we don't have such kind of situation in gauge theory because all the coupling constant dimensionless. Here, for dimension 4 coupling. But if this diagram has infinite divergences, then, to my opinion, you're more or less in the scenario which I described previously, namely that if you start continuing adding more and more particles, for example, like that or like this, no possible ways, you will enhance infinite divergences. So therefore, your amplitude in this particular setup will blow up order by order. And if they blow up order by order, if you remove infinite cutoff, then you're exactly in one of those scenarios which I mentioned, which means that if you resum those divergences, you're bound to get 0.
So is it 4D or does it matter?
If you wait for 4D, there is no divergence. The divergence will appear only in 4D.
Because there is some view that happens in cosmology that as things are getting stretched, we try to probe the very infrared. Things are getting positively disconnected, so the theory is actually becoming lower dimensional. Whether these two things compete and they cure the infrared divergence.
You should be careful. It's true that once you go to this expanded universe, you effectively reducing number of dimensions you're filling. But it doesn't prevent you for have Fred divergences appear, because the Fred divergences, they come from the exchanging of the particles whose wavelengths could be arbitrarily large, like size of the universe. So even though, for example, you have some particles which are expanding, which move apart with the velocity of light, they could still exchange, they fill each other by exchanging of particles.
Do we have more questions?
So maybe follow up. So even the notion of massless particles is a bit blurry in cosmology. You would say that the particles that oscillates, mass or their Hubble, or what is it called, mass flat space, and anything lower than Hubble falls under the umbrella of massless particles.
Yes.
So maybe for all of these, I mean, when we see that the stochastic effects are large, that's smaller than Hubble, not necessarily mass. So it could be that the problem plagues all of the models, not necessarily just
No, but to add to this, coming back to what Grammatics made previously, that strictly speaking, in quantum computing, the cosmology correlators. There is no particles which are on shell per se. So when computing the diagram, because you have finite time propagation of particles, there is no even notion of particle being constant only. But what this relation basically tells you that okay, imagine you computed this diagram, including also particles, etc. What it will tell you is 0, which appears here, basically will tell you that because of the divergence of percent, analytical properties root level of this correlator will be slightly different compared to those which you would expect naively. What I mean that instead of having simple pole, you might have some additional function like logarithms of this energy and some power which will appear in this object, such that after you take this continuity, it will be simple pole. It will be something which definitely won't have the decay. So, which is another way of saying that even though here you don't have percent for divergences, but if particle propagates sufficiently long time, it's not on shell, but it's close to on shell. It's almost on shell. And this is almost what will serve a Fred regulator. So this evolution time, if you wish, somehow it should propagate into formula to replace infrared cutoff. So you're expecting it's not infrared divergence per se, but it will kind of echo those divergences, where your evolution time will replace infrared cutoff.
Thank you very much.